My name is Abdullah Vohra, and today I am excited to share with you a lab report on a fascinating topic, the refractive index of water. In this video, we'll dive into the concept of refractive index, why it's important and how we measure it in a university laboratory. I'll walk you through the entire experiment from setup to results and explain the science behind it in an easy to understand way. So let's get started. Before we jump into the experiment, let's go over what we are trying to achieve and the science behind it. Firstly, the objectives. Our goal today is to measure the refractive index of water using Snell's law and a laser beam. The theory behind this is when a light travels from one medium to another, its speed changes, which makes the light bend at the point where two media meet. This bending is described by Snell's law, which can be written as n1 sine theta 1 is equals to n2 sine theta 2, where n1 and n2 is the refractive indexes of the two media. We have using n1 as a refractive index of air and n2 as a refractive index of water, where theta 1 is the incidence angle and the theta 2 is the refraction angle. In our case, light is moving from air, which has a refractive index of 1 into. By measuring the angle of incidence and the refraction, we can figure out the refractive index of water. Now that we have covered the objective and the basic theory, let's talk a look at how we set up at the experiment. Now let's take a look at the apparatus we will be using for our experiment. A laser pointer, a red laser pointer with a wavelength from 620 to 750 nanometer to provide a precise beam of light, protector to measure angles accurately, a transparent container to hold the water obviously as the medium whose refractive index we are measuring, a ruler for additional measurement if needed, paper and pen to record our observation results. The first diagram that you can see shows how the experiment works. We have a laser beam passing from air into the water. The angle at which light enters the water is called the angle of incidence, and the angle at which the light bends inside the water is called the angle of refraction. By measuring these angles, we can apply Snell's law to find the refractive index of water. The next photo you can see is our live setup. As you can see, we have the laser pointer positioned to shine a beam at the surface of the water in the transparent container. We have set up a protector to measure the angle of incidence and refraction. With this arrangement, we can accurately determine the necessary angles to calculate the refractive index of water. Now let's go through the setup and the procedure of our experiment step by step. First, we fill our transparent container with water and place it on a flat surface. To make it easier to see the laser beam, we place a piece of paper behind the container, as you can see in the last implementation diagram. Next, we shine the laser pointer at the surface of the water at an angle. We mark the point where the laser enters the water. This point gives us the angle of incidence denoted as theta 1. We then observe and mark the point where the laser beam exits the water. This gives us the angle of refraction denoted as theta 2. Using a protector, we measure the angle of incidence theta 1 and refraction theta 2 precisely. Finally, we apply Snell's law to calculate the refractive index of water. Since we know n1 of refractive index of air, which is 1, we have measured theta 1 and theta 2, which are the angle of incidence and the angle of refraction. We can solve for n2, the refractive index of water, using Snell's law. Let's see this in action in the next videos. Let's take a look at our live setup and see how we took our readings from the experiment. In the first video, you can see our experimental setup in action. We have the transparent container filled with water and the laser pointer positioned to shine a beam at an angle in the water. we use a protector to measure the angle of incidence theta 1 where the laser beam enters the water. We then mark the point where the beam exits the water to measure the angle of refraction. By recording these angles, we are able to apply Snell's law to determine the refractive index of water. In the next video, to your right, next we explore a fascinating phenomenon called total internal reflection or TIR. In the second video, we demonstrate total internal reflection when the laser beam hits the water surface at a certain angle, which is our critical angle. Instead of passing through, it reflects entirely back into the water. This happens when the angle of incidence exceeds our critical angle. Total internal reflection occurs when light travels from a medium with a higher refractive index to one with a lower refractive index, like from water to air. If the angle of incidence is greater than critical angle, the light does not exit the water but is completely reflected back inside. As there you have it, we have covered the setup, the process of measuring angles to find the refractive index of water, and the intriguing phenomenon of total internal reflection. Let's move on to discuss our results and conclusion. Now, let's take a look at the readings we have obtained from our experiment and see how we calculated the refractive index of water. Here are the readings we took. During our experiment, we measured the angle of incidence and the corresponding angle of refraction for 4 different trials. Let's look at the table. Now, using these angles, we can apply Snell's law to calculate the refractive index for each trial. As you can see, for the first trial, we have N1, obviously it's refractive index of air, so it's 1, and theta 1 is 30 degrees and theta 2 is 23 degrees. Implementing that in our Snell's law, we get the refractive index of water as 1.34, and we repeat these four times. Refractive index for each of our 4 trials and obtain the following values. To find the average refractive index, we take the mean of these individuals' measurement. So the average refractive index of water from our experiment is 1.32. The experimental result shows the refractive index of water is approximately 1.32, which is very close to the known value of refractive index of water, which is around 1.33. The slight discrepancies between our measurements and the known value can be attributed to various experimental errors, which will be discussed further. Overall, our experiment was successful in demonstrating the measurement of the refractive index of water and confirmed that our method aligns well with the established scientific value. Before we conclude, it's important to highlight some precautions we took during the experiment and discuss potential source of error. Precautions are laser alignment. Ensure the laser pointer is aligned correctly and point directly at the water surface at the desired angle. This ensures accurate angle measurements. Stable surface. Place the transparent container on a stable surface and level surface to avoid any movement that could affect the measurements. Avoid parallax error. Make sure the observer's eyes is level with the marks being made at the paper to avoid any parallax error in the angle measurement. Repeat measurements. Conduct multiple trials for each of angle of incidence to ensure consistency and reliability of data. Source of error. Measurement inaccuracy. Error in measuring the angles of incidence and refraction can lead to incorrect calculations of refractive index. The precision of the protector used can limit the accuracy of angle measurement. Using a more precise protector can help reduce this error. Subjective judgment in marking the laser entry and the exit positions and the leading protector can introduce error. Taking multiple measurements and averaging them can help minimizing this issue. To the end of our journey into the fascinating world of optics and the refractive index of water. I hope this experiment has sparked your curiosity and shed some light onto the principle of light refraction. Remember, science is all about exploration and discovery, so don't hesitate to conduct your own experiment and delve deeper into the mysteries of the universe. Thank you for joining me today. Stay curious, stay inspired, and keep exploring. Until next time, take care and happy experimenting.